Thank you very much then for this nice introduction, and thank you for inviting me in Brazil to give this talk at this school. I'm very happy to be here. So, as he said, I'm working in CNRS in Toulouse, and these last 5 years I was also working in Saragossa together with Raoul that you heard yesterday. So part of the presentation I made there on holography, experiment, etc. has been achieved and done with these guys, Cesar Machen and Luis Alfredo Rodriguez, two PhD students, common with Cesar and myself. So I'm going to talk about electron holography and also Lorentz microscopy. This Lorentz microscopy will be for tomorrow. But first, you probably know, after more than a week of TM, that TM is a very efficient tool for, where is my best place to make the presentation? I don't know, maybe here, is it okay? For images, and then you can have a nice and interesting TM images in a conventional bright field dark field imaging mode or high resolution mode like it is, or even high resolution STEM mode, but that you probably already heard, or you will. Electron microscopy also is a very efficient tool for local chemical determination, either in energy electron loss spectroscopy or even making FTEM, energy filtered TM images, or EDX as well. I guess you will have a second lecture by Raoul this afternoon. But what I'm going to speak here is I will try to say that with TM you can also map local fields. So we are not speaking about spectroscopy or imaging, of structural imaging, but we are dealing about fields, meaning electrostatic fields, magnetic fields, and even strain field. And this is electron holography. So my main purpose here is to show you how we can use TM in this electron holography mode to extract information on fields. So first, what are rapid electrons? You know that electrons are particles, so they have a given mass, a kinetic energy, they have an electric charge, and there are given potential, they have electrostatic energy, potential energy. They are sensitive to electrostatic force, they are sensitive to magnetic force, they can interact with the electron cloud and the nucleus of atoms. This is a different diffusion than diffractions, and they can be localized, are particles. But they are also waves. And our waves, they have the electron beam as a wavelength. The electrons cannot be localized. They are diffracted by a periodical lattice. This is the reason why we get diffractions. And they can create interferences. So this is kind of this is the common question that physics asks. And then if there are waves, there are different kind of waves. Either they are spherical waves, or they are plane waves. In the case of electron beam, you have a plane wave with an extended source in the gun, and then you have a plane wave going through the columns. And if you have a plane wave, you can describe this plane wave with an amplitude term and a propagation term, and in the propagation term, you have this phase term. So if electrons are wave, they are supposed to be sensitive to interfere between them. And you can even think about having this young Fringes experiment with electrons. And indeed, you can do it. And in the TM, the way you do it is not with some holes, but with a prism. And you have this electron wave arriving on this prism. And then this prism bends each part of the electron wave passing on each side of this prism. And then they move to superimpose and create interferences. And actually, the way the biprism is done in a TM, but I will go in detail later on, is with a little wire that you positively charge, and then it bends the two parts of the electron beam passing on each side of these wires to create an interference. So this is a movie. This is a movie done by...
Bright spots appear here and there. These spots indicate...
You probably do not hear the guy, but the guy is Tonomura, a very famous Japanese researcher who make a lot of in electron holography, and it's just saying what you read there. So typically what you are observing is a screen on which electrons are arriving, and then making some spot each time they beat the detector. So the whole experiment holds for about 30 minutes, so it will be speed up at a certain times. But what you see is the impact of the electron on the detector. And you imagine that you have a kind of homogeneous distribution. Well, the experiment has been done with a biprism. Okay, the experiment I described just before. So you have two beams coming on the detectors. And after 30 minutes, something like that, you start to see fringes. So for me, it's something which is fascinating and probably that you cannot understand clearly, but you have impact, so you have electrons, so there are particles, and then you are making that for 30 minutes, and then you have fringes, so there are waves. So this is the main question in physics, I guess. So we are dealing with something like particles, well known, and mechanical quantum mechanics, there are waves. Whatever we are doing with the waves. So just to let you know that there are still things which I don't believe is, what I think is not so clear. Whatever we are working with. So what's happening in the electron wave in a TM? As I said, we have the source. This is on the gun, and you have this plane wave arriving on the object, okay, interacting with the object. This plane wave is modified both in amplitude and phase because of interaction with the electrons with the materials, and I will go in details on this term. And after the beam is passing through all the optical elements of the columns, mainly the objective, so it's modified again by the transfer function of the objective, and then you have some additional phase shift. And then you go down to the detector, and in the detector you are condensing the beam, and then you don't get this complex wave, of course. You just get the square of this one, and then you get only the amplitude term. And the phase is lost, okay? So all the electron holography and Lorentz microscopy goal will to find a way to have this phase term back. And the way to do that is, okay, you imagine your column as well, and then you split the beam in two parts. One is passing in the vacuum, one is passing on the sample. And then with this biprism, which is what I explained you rapidly previously, just a little wire that you polarize there in the column. It's located in the SA aperture, selected aperture plane, in the image plane actually. You bend each part of this beam, the beam which has been passing and interact with the sample, the beam which has been passing in the vacuum, and then you create some overlap. And then this overlap creates fringes, like in a Tomura experiment, but it creates fringes with a beam, a reference beam, and a beam that has been phase shifted. Okay, and then if you make the calculation of what is the intensity of this electron hologram, then it corresponds to the sum of this reference wave, which passed in the vacuum, plus the phase which has been phase shifted after interaction, okay, plus some background, square, and then if you develop that, you get this equation, which gives you fringes of periodicity 2 pi R0, which depend on the voltage applied on the biprism, plus this phase shift term. And this phase shift term is exactly the phase shift term of the electron wave after interaction with the materials. So I will go in detail after. So I just tell you that, okay, when you have a beam passing through materials, electron wave, electron beam is modified in amplitude and phase. And during my lecture, I will detail all the different phase shift that the beam feel when interacting with materials. So the first, if you have a beam interacting with some kind of electric materials, electrostatic, like a diode or a PN junction, you will have some interaction between the electrostatic field and the beam, and you get a phase, what we call an electric phase shift. If you have materials interacting with magnetic materials, domains, you will have also some magnetic phase shift. With a crystalline material, you already know that. And the geometric phase is when you have materials of different parameters, then the phase of the diffracted beam will change. And thanks to measuring all these phase terms, you should be able to map the local electrostatic field, the local magnetic field, the crystal structures that everybody knows, and the strain field. And that will be the object of my lecture. So how did it go? This is a microscope, FEI microscope, Techni. We are doing holography on this microscope, and in the image plane there, where we put the selected aperture, actually you add on the system to support the selected aperture, one with a little wire, which can be barely seen there, you see, and you are polarizing these wires with voltage up to 100, 200 volt, and then the part of the beam which passes above it and below it will be bended and then overlap to create the hologram. So holograms means interference. You know that you cannot do interference with that kind of light. If you want to, in optics, if you want to have interference, you need to have coherent beam. So you need to use laser in optics. For electron microscope, there is different type of electron source. You know, you have the tungsten one, you have the lattice one, you have the Schottky FEG, you have the cold FEG sources. So you have four type of electron sources. Each of them have particular properties. For instance, the more intense one is a lattice, or the tungsten is even much more intense. But the brighter one is a cold FEG. Brighter means very coherent beam. It means like this ampoule. These ampoules are very intense. This laser is not intense at all, you see, but it's very bright. Okay, it's very bright because it's very coherent. Okay, very teeny dispersion, energy dispersion. But you cannot light a whole room with that. You need to have this lamp. Okay, if you want to do interference, you need to have a laser. You cannot do interference with this kind of lamp. Same thing with electron microscope. If you want to have interferogram, to make interference, you need to have a coherent source. So you need to have a field emission gun, okay? Either a Schottky or even better, a cold FEG sources. Because if you, what we call the brilliance is much higher, and the energy dispersion is even much higher in the case of the FEG, okay? So this is, you know what is a FEG, and it's just a little teeny tungsten tip, and you extract electron applying a high voltage between the tip and the anode, and you extract electron by this emission field. While in the case of thermoionic sources, you are heating the tip, and you have spread electrons which are emitted with a quite large energy dispersion. And if you use this kind of gun to just observe the Fresnel fringes you get from an aperture, you observe a important number of fringes up to which indicate that this source is much more coherent. And if you want to have an even better coherence, you have to work in a particular condition. Normally, when you are using a TM, you have a beam. You take a round beam, and you try to have a kind of a homogeneous intensity distribution over the image, using the spreading of the beam, using the astigmatism of the condenser. In a case of electron holography, what you want to do, you want to have like a very astigmat illumination, like that, and you have these interferent fringes. You put the biprism here in order to have overlap of these two parts and have fringes, which are very good contrast here. The last, not the last, one also important thing is that when you are making electron holography, you want to measure the phase shift of the electron beam after interacting with the field you are interested in. You have additional phase shift that occur when the electron is interacting with crystalline materials. There are some dynamical effects due to particular diffraction condition, that you have to avoid, because in this case, if you have some diffraction contrast that you observe in your image, you will have some artifact in the phase measurement. I will go there in detail. What you need as well is adjusting the polarization of the biprism to have sufficient contrast. What you see there is the different interference fringes, holograms. They are similar, and they are synonym. As a function of the voltage you are putting on a biprism. I will just go back. You understand that when you do that, you apply the voltage here to bend these two parts of the beam passing on each side of the biprism. The higher the voltage you apply there, the higher the bending, and then the smaller the interference fringes. But you have also, I will show you, some contrast that shut down. Okay, so what I show now is that if you don't apply any voltage, you just the Fresnel fringes of the biprism. If you increase the voltage, you have fringes that appear over a distance that we will call overlap. And if you increase even more the voltage, you increase this overlap, okay, by quite large, but you decrease the interference fringes, and you decrease as well the contrast of these fringes. You see that the contrast is very good, that you should be able to measure the phase shift of these fringes easily, while here it's going to be more complicated. So you need to have a compromise between the biprism voltage you apply here that will give some contrast and interference distance. You can see that this is the beam, the sample. You are applying a voltage here in order to bend this part and to overlap with this part of the electron that go in the vacuum. Okay? And then you obtain some holograms here, which are given interferences and a given width. It corresponds if you can imagine that these two beams come from two virtual sources, okay, which will be geometrically, you can draw them, and this will be this one. If you increase the voltage here, it will bend even more, and then it's come just like if you put the source even more away, apart from them, and then you increase a lot the width of the hologram. So if you want to work on a tiny materials, on the larger materials, maybe the part of the materials the material is too large, and you have to increase the overlap in order to study the whole system. So you have to increase the biprism, but then doing so, you are decreasing the contrast as well. Okay, so this is these two young fringes, I would say, two sources, which give to these two holograms. Okay, and as I said, if you increase the biprism, you increase this distance, you increase this beta angle, you increase the overlap width, okay, but you decrease the interference fringes and you decrease the contrast. Okay, and this is some results that you get practically. These are holograms obtained, I don't know who did that, with different applied voltage. And what has been plotted here is the decay of the fringe contrast there, down to about 10% at 80 volts, with the decay in parallel with the fringe spacing, okay? This is for a particular regime, and this is for another type of regime as well. And you see as well that when you go up this voltage, you have almost 2-3% of contrast, so you cannot do anything with that. Maybe this one is too complicated, but I will just make a brief introduction to that, because to overpass this problem, people in Hitachi, actually, Japan, in the Tonomura group, have built this new microscope with 2 biprism. And I will try just to show you. It's okay if you forget it. It's just you know that you can think, when you are doing that, you have to think the microscope as a kind of optical bank, okay, in which you have a source, you have different optical elements, lenses, etc. And you have biprism, and you can play with. You know, people doing optics are used to that. They have lenses, they have different elements, and they adapt it in order to make something with the light in that case. In a microscope, it's a kind of more complicated because we are in the vacuum. It's not so evident to remove a lens and to put something. Whatever, in some companies or laboratory, people are capable to modify that. And this is what this guy has done, and I find it interesting. Actually, what they don't put only a biprism, as we are, but two biprism. And this is, okay, the source, the sample, okay, and then you are again overlapping the blue part, which is the reference one, with the part which has been phase shifted. And in this configuration, you have a biprism here, small biprism, that bend a little, and another biprism that bend a little more. So you have two biprism. In that case, you get this kind of overlap with a given interference fringes. If you increase only the biprism here, you see that you just increase this angle and you overlap, you increase the overlap distance here, so the width of the interference without changing the hologram, without changing the interference fringes. Okay? In the other condition, if you increase this biprism, so have a look to the configuration, you are keeping the same overlap, but you are decreasing the interference fringes. So, as I said, forget about this drawing, which is maybe too much specialized. What I just want to say that in some case, you can adapt your optical configuration in such a way that you can increase the overlap width, okay, of your hologram, keeping the same interference fringes, or changing the value of the other biprism, keeping the overlap width constant, and changing the interference fringes. So it's the reason why I said in dedicated experiment, you can do more or less whatever you want. For instance, in the microscope that we have in Toulouse, that we recently had 2 years ago, which is a dedicated Atashi microscope, fitted with a Colfeg gun, and is fitted with actually 4 biprism. One biprism is located just below the gun, and 3 are located in the optical column below the objective, like I was explaining previously. The advantage of this biprism there is that you can, normally you arrive with one single beam interacting, and then you overlap, and then you make some superimposition. Here, with the biprism on the top of the column, you arrive with the beam and you can split the beam. And then you split the beam, and you have then 2 beams arriving on your sample. So either you recombine them or whatever, you do whatever you want. So in this microscope, we have not 1 electron beam, we have 2 electron beams, but coming from the single source. So they are coherent. You understand? Okay. So this is the typical microscope that we order with Hitachi. We have discussion with them in order to build this unique microscope, and we design it with this idea of having, I would say, an optical bench, not a microscope. So you can modify many things on that microscope. Okay. So now, as I explained you can overlap the beam which is passed in the vacuum, the reference beam, with the beam which has been phase shifted after interaction with the materials, and then you get an holograms. And as I said, the holograms contain some periodic contrast with a phase shift which is directly related to the phase shift of the electron beam after interaction with the sample. And I say that this phase shift is depending on the electrostatic and the magnetic potential, and actually this is the Aharonov-Bohm equation, which show that when interacting with electromagnetic field, and meaning electrostatic potential and magnetic vector potential, the little arrow should be there, the beam, the electron wave is phase shifted, and this phase shift is directly related to the electrostatic potential contribution to the phase shift, okay, and to a magnetic contribution to the phase shift. So you have an electron wave arriving on the electrostatic potential and a magnetic vector potential is phase shifted, and the phase shift is directly related to these two components, okay? So when you want to work on that, if you have a non-magnetic materials, the phase shift is directly related to this electrostatic potential, to the mean potential. So, and in a case of magnetic materials, but we will see it tomorrow, we have to find a way to separate this contribution to this one in order to determine the magnetic contribution only. So this is an image of the plane wave arriving on a given sample, okay? The sample you are illuminating with your electron beam is made of cations and electrons, etc. So they have charges, clouds of charges, and positive charges, the cation, okay? And then the electron beam is sensitive to that, and then is phase shifted after interaction, and this is the phase shift you get from the electrostatic potential. In the case of the magnetic materials, following the Aharonov-Bohm effect, so you have the magnetic material there and the stray field around it, okay? And then the wave, the plane wave is interacting with this magnetic field following this equation and is phase shifted like I saw there. And as I said previously, the point is if you have magnetic materials, you also have electrostatic field, so you have a phase shift which corresponds to the sum of both of them. Something regarding the phase shift induced by the magnetic field, the electron is sensitive only to the component of the magnetic field which are perpendicular to the propagation direction, okay? You can think like it is similar to the Lorentz force, okay? You have electrons, and then you have magnetic field, and then the electron is only sensitive to the Lorentz force only acts on the electrons with the combination of the magnetic field which is perpendicular to the displacement. So we get the holograms. Oops. So the hologram is something like that. Okay, this is the image of an hologram obtained on these little nanocubes. And the goal will be to extract both the amplitude and the phase, and the way we are doing that is going by the Fourier analysis. So we make the Fourier transform of these holograms, and then we get these two spots which correspond to these fringes, which are the fringes of the hologram, the interference fringes. You see that the fringes are bending close to the materials. If they are bending, it means that they phase shift, and this is actually the phase shift of these interference fringes that we are interested in. Okay, so you make a mask, and you make a Fourier transform, an inverse Fourier transform of it, and then by numerically you can separate in the inverse Fourier transform of the Fourier transform the amplitude image and the phase image. Okay, you extract separately this term and this one. So the amplitude image is just the basic TM image you will obtain if you are not doing any interferences. So what you get here is the TM image of these two systems, okay, of these two. And in addition, you have what we are looking for to this phase image, okay. So the phase outside of the materials is almost zero. It's not exactly zero. I will tell you why in a little. And you have some value in the middle, okay. It means that you have this electrostatic contribution. This is iron, so the material, the electron wave is phase shifted after interacting. And then what you can do, and I will discuss that mostly tomorrow, you can separate the electrostatic contribution and the magnetic contribution. Okay, so as I said, the phase contains this electrostatic contribution and the magnetic contribution because these are magnetic, this is iron. And then I will show you the way tomorrow, as I said, to separate them. But today, during the end of this lecture, I will focus first on using electron holography to measure electrostatic fields. Okay? Oh, just something you can redraw this looking to the curve. Oops, sorry. And this, what you see here is the magnetic flux going out of this little cube. But as I said, magnetism is for tomorrow. So, we're going to work today only on this term. Okay, the total phase shift is electrostatic plus magnetic, but we're going to work only on this one. So you have a plane wave arriving on a given sample, and it's phase shifted due to the fact that the materials is composed by cations, so there are charges, there are etc. And this electron wave is sensitive to these charges. So what do an electron? What does an electron? No, what do an electron see when? What does an electron see when entering a crystal? There is two. You probably have heard that. Either you have a thick materials and dense materials, and then the wave is the amplitude of the wave is decreasing because of absorption, and then you have kind of an amplitude object. In the case of thin materials and not so dense materials, you have the so-called pure phase objects, meaning that there is no absorption of electrons, and you get the same intensity of the beam after interacting with the materials. But the wave has been phase shifted. It is a pure phase object. Okay. Most of the time when people are dealing and trying to simulate TM image, high resolution TM images, they are in this case. Okay, they're looking to the pure phase object. And actually, what do an electron see when passing to this material? As I said, is the potential of the materials, the so-called mean inner potential of the materials, which correspond to all the electrostatic field he saw when passing through it. And actually, he saw a positive field. So the electrons are accelerated. The phase is putting forward the electron. Okay, and then which is similar to when you have an optic beam passing through a transparent materials, then you have this index of refraction, the index of refraction, okay, the N, which just the ratio between the speed of the light in the vacuum and in the materials, okay, this refractive indices. In the term of electron is the same, but this indices is the mean inner potential. Okay, what you are getting here then is the measures of the mean inner potential. So if you have a beam passing through this material of a given thickness, you are integrating this electrostatic potential along the thickness of the material the beam is passing through. And then if the material is homogeneous in the thickness, if you have only one type of materials, you get this, with this constant factor, you get this mean inner potential times the thickness of the materials. Okay, in case of the system is homogeneous. C is electrostatic is a constant which depends on the electron wavelength, the kinetic energy of the electron, and the rest mass energy of the electrons. And this is the value of C. So what I tell you there is that with this term, you should be able to measure this mean inner potential. Okay. In case, as I said, of some electrostatic device like junction PN or whatever, or even charged particles, I will show you something on that. The electrostatic potential, the electron fields when interacting with the materials is not only the mean inner potential, so the material itself, but possible local electrostatic potential. If you have a PN junction, you have a local field, okay, electrostatic field between the two doped regions, and then you should be able to feel it and then to measure it. And as I said again, if these two mean inner potential and local potential are constant along the beam direction, then the phase is just these two potential times the sample thickness. And if you want to measure, to give quantitative measurement of something, the potential, then you know to know perfectly the thickness. So either you use an alternative method to measure accurately the thickness of the material you are interested in, like using seabed or working with materials of a given shape, well known, either a sphere or a cube, etc., or a cleaved sample that you can determine exactly which thickness is. And then you can quantify the mean inner potential and the local potential. So the mean inner potential, as I said, is the electrostatic potential the electron see when passing through the sample. And then it has been calculated or theoretically by different people. It then depends on the number of atoms of a given type, okay, with a given scattering factor, okay, which is this value. So you are making the sum over the unit cell of the different atom you have in the cell, okay, with a given scattering factor, time this constant with the volume cell and the volume of the unit cell, the mass of the electron mass, etc. Okay, whatever. There is just, people are not so, this is a complicated calculation because either you think about isolated atoms, so you have material with you have a silicon atom, for instance. A silicon atom, you know what is the number of mass you have in it, you know the mass, the number of proton, neutron, etc. So you can determine that in a pure silicon. If you also add that in your materials you have delocalized electrons, it means that you have no more just a single atoms, which is cloud around, but the atoms with cloud of electrons which are distributed over the world's materials, okay? So depending on whether you consider this electron redistribution or if you consider just atom with its own electron clouds, you will have different mean inner potential. And then you see the difference could be sometimes huge if you take GAN. So there is many numbers on this mean inner potential, theoretical numbers, and complicated to really determine by electronography. Whatever, this could be, electronography could be used because if you are capable to measure that and measure the thickness, you will have information about this mean inner potential. And then there is some attempt of trying to find experimentally by electronography some precise measurement of the mean inner potential in various materials. And they are sometimes fitting with this isolated or with these models. Well, whatever. Whatever, if in this electrostatic system you phase measurement, you get this constant times the mean inner potential times the thickness. And if you want either to know that or you want to determine the shape, meaning the thickness, you can use this electronography. For instance, this is an iron nickel sphere, okay, and this is an neurogram obtained on this sphere. And you see, actually, if you make a zoom on this part, that you have the bending of these fringes. So bending means you are looking to this phase shift of this center fringe in the vacuum and when entering in the materials. And this is the phase you extract from that. Okay, so this is the image of that. And with that, you can directly see that you have a perfect sphere profile. Okay, so with this sphere profile, you can fit either the mean inner potential, then you can use it for composition analysis, or you can even make some morphological studies. Okay, we know that this is a sphere. This is confirmed that this is a sphere. So you have a projection of the world structures, and then you can fit it to determine the morphology of your material, etc. So this is an example, very basic example. Another example, it's a tetrapod. So you have a kind of tetrapod of magnetite, so like a structure like that. you make an hologram on that, you extract the phase, and from the phase, assuming that you have a pure materials, meaning the mean inner potential is constant for the materials, whatever the thickness, you have some phase, something which is proportional to the thickness. So you can have a 3D shape type of your materials. Okay, let me have a little water. So I show you in the very last example, in the two very last examples, something that we extracted only considering the mean inner potential without thinking about any additional electrostatic potential due to charge effect or due to the fact that you have an electronic kind of a device with like a CMOS transistor or diode or PN junction or things like that. So if I go back to my two cubes, we were dealing with that. And what you see here, I said that in a vacuum, the electrostatic potential should be 0. In a vacuum, you have no materials. Okay, you have no materials. Then the phase shift should be constant and 0. And if you have to look a close look on these images, you see this is not 0 in the vacuum. You see, you have some change of contrast. It's a green, but varying. And actually, what's happened here is that these two particles are charged because the electron beam is interacting with these materials, and then you have secondary electrons, then the system keeps some charges. And if you have a charge in an isolated materials, then you have an electrostatic field shining around it. And then if we are capable to measure this phase shift around it, we should be able to measure the charge within these materials. And this is what has been done here. So this is another example. This is MgO cubes. This is an hologram. And this is the phase image, electrostatic phase image, extracted from this hologram. And you see that in a vacuum, okay, you have some phase shifts, which are related to the fact that you have an electrostatic field radiated around this nanocube due to electric charges trapped in these nanostructures. Okay? The question is, can we measure the field? And if we are capable to measure the field, can we measure the number of charge we have trapped in this nanocube? So let's go to the very basic of physics, not so basic, but it is what is the effect of a given charge? What is the relation, I would say, between the given charge located at the given position with the electrostatic field around it? And this is the Gauss Theorem that you can rewrite it like that. What's it? And then if you make the gradient of this one, you have a relation between the charge, okay, and the electrostatic potential, okay? In holography, we are measuring this electrostatic potential. So if we combine all these equations, we can make a direct link between the charge responsible for the electrostatic field, which is shined around this particle in which you have some charge, and the phase shift that you are capable to determine with electron holography. And the way to do that is to make some contour around the given, on the phase image, around the given region of this phase image, and then you extract the number of charges pinned there. I will show you right now. So again, this is the hologram. This is the amplitude image extracted, so the TEM image, and this is the phase image, which corresponds to the electrostatic phase shift associated to charges trapped there. And so what we do, we use this phase image, determine a contour, okay, and then we are integrating following this equation extracted from the Gauss Theorem. And when we make the measurement along this contour, okay, following that, we get one point, which gives you the number of charges which are trapped in this region. And then you move, and then for each region, you make this, this integration along the contour, and then you plot everything. When you arrive in the vacuum, out of the MGO, there is no more charge trapped, so you get something which is constant. And then what you determine is that in this region of the nanocube, you have 50 positive charge which are trapped, okay? This is what you get. And what we see here is that we have some kind of a jump. So we can even go a bit more in details. What's happened at the very last region, where you have the surface of the cube, you have 10 positive charge. So imagine you have a cube, okay, which is a cube. Well, this is a cube. When you are coming with your electrons, you are making this hologram analysis, and from the phase image, you are making some contours, and in the contour, you observe that you have n charges, and then you increase the size of the contour, and you observe another number of charges, etc., etc. When you arrive to the very late surface of the cube, you have just one important step. Why? Because actually this is an insulating cube, an insulating material. So charges are located on the surface of the materials. So when you are measuring the charges there, you are measuring the charges which are located on the surface of the cube, and you have more and more and more charges. And at the very last surfaces, you are integrating all the charges which are located on this surface, on the very last surface. And this is the 10 charges that you get there. You can be sure of that. Okay? If you have some surface density of given sigma surface density, on these regions you have 4A, A being the size of the cube, DZ, this is the size of this surface. And then you have A2, okay? So if you have a surface density of sigma, the slope here will give you the number of charge if as you move from this point to this point, and when you arrive to this point, you are getting in addition all the charges located to these surfaces, and this is what you get. Get a surface density. When you make this analysis of this curve, you now observe a surface density of 1.9 10 to the minus 3 charges per nanometer square. And if you go at the very far here, you get, the value expected at the very last surface, about 10 charges. So what we demonstrate here is not only that we have 50 charge on this cube, which are trapped, which are created by the electron beam and trapped in this cube, and these charges are located on the surface of the cube. And this is thanks to the study of the electrostatic field, which is shine in the vacuum, due to this charges which are trapped. So we did similar thing on different cube, and for instance, the smallest one we get is about we have been able to determine the appearance of about 5 charges in a given material. So this is the sensitivity of the method when measuring something, about 5 elementary charges. Another experiment I will show you here again on the electrostatic measurement is an in situ experiment. So previously, I was just showing that with electron holography, you should be able to measure charges in different devices, and this was on a carbon nanocube and a MgO cube. But you may think about, other kind of device when you have charges which are localized in some part. And here we have been doing something different. We are working on a field emission gun, and practically we are working on the emission of electrons using a carbon nanotube. So you know what is a carbon nanotube. Well, these are quite different. This is carbon nanocone. So in a carbon nanotube, okay, let's go. What we want to do, we want to use a carbon nanocone as the sources for emitting electrons in a cold phase, in a field emission microscope. There were attempts already time ago on using carbon nanotube to make this kind of sources, but people have seen that the carbon nanotube were not very stable because it's a very teeny one, and that they were moving in the gun, so they was not a very good and efficient. In our lab, there is a group who did this carbon nanocone, which was, it's a cone. It's much more robust. It doesn't vibrate. So we try to use it as a new field emitter, to new electron sources. And then we do an experiment inside the TM. So as I said at the very beginning of my talk, there is different kind of electron source. One is the cold phase. The cold phase, you have a tip, and you extract electron by applying a voltage between the tip and the anode. And then you extract electrons by the huge voltage you are applying there. And the calculation have shown that if you use a carbon nanocone or whatever, you have even much brighter sources. So we are thinking about using it for electron sources. So in the TM, we use dedicated stages which allow to put this carbon nanocone, okay, in front of an anode, and we will apply a huge voltage between this cone, okay, and the anode in order to increase the voltage here up to the regime where you extract electrons and you have field emission like it occurs in a TM or whatever, okay? So this is the system. So this is a nanofactory holder. Maybe you know this company, which is a breakdown actually. So you have your carbon nanocone here, and you have the anode. You apply the voltage, and what we are doing, we are looking by electron holography. We will work by electron holography to see how is the field around the tip, okay, for the different regime. In a parallel, we are capable to measure the current, okay. And this is what you get. You are measuring the current which is emitted by the tip when increasing the voltage. So if you increase the voltage, at a given voltage, hop, the current is starting because you reach the point where the voltage is sufficient to extract the electrons and close the circuit. So this is the experiment. You have this carbon nanocone. This is the hologram, okay? And for zero applied potential, so you did not apply any voltage yet, you have these phase images. On the phase image, you have the zero in the vacuum, and you have only some phase contrast, some contrast in the phase image here, which just correspond to the mean inner potential of the material, okay? Well, we talk about this mean inner potential. So you get the image of the tip. And this is the amplitude image, useless. And then you increase the voltage. You increase the voltage, so you put 10 volts between this point and the anode, which is far away from the board, but okay. Well, actually, I guess the anode is just almost there. And then you see in the vacuum some electrostatic field due to the fact that you have put a voltage between this point and this point. And in addition to the mean inner potential, but you can remove the inner potential. The mean inner potential doesn't change, so you can make some image analysis and subtract from this one this image which contains the mean inner potential, and then you have only the electrostatic field which is generated at the tip by the voltage. The phase image, phase is 0 to pi, 0 to pi, 0 to pi, so you have this contrast, jump in the contrast, which corresponds to this jump when you go from 0 to 2 pi, then 0, etc. But you can use some complicated, actually, codes to remove this jump and unwrap the image. So this is the unwrapped image. These are the same, but what you avoid this jump due to 0 2 pi step. And then you get this value of at 10 volt. Okay, so 0. What we're going to do, we're going to apply an voltage, increased voltage, and we will see, and we will measure how many charges are pinned in this carbon nanocone, okay? You have 0 volt. You have just a minimum potential. So you have 0, 0. If you applied 10 volt, you can make the analysis I just saw previously, and then you measure the number of electrons you have in your tip. The tip is there, okay? So the number of electrons you have to the tip, and then you have no more electrons there, okay? So in this curve, this direction is the direction, is this direction, I mean, along the nanocone, but the nanocone is stopped there. So this is in a vacuum. This is the number of charge you have on the nanocone for a given voltage, here 0, so no charges, and then you have 10 volt, and then you have some charges that appear, and there are more at the very tip of the nanocone. And then you increase. So what you see here is the increase of the voltage, the increase of the electric field as a function, the increase of the electric field, yes, in the vacuum as a function of the voltage you are applying. And then in parallel to that, you have an increase, I will show it again, increase of the number of electrons that you are putting in your nanocone until the time you reach the value for which electrons are emitted. Okay, so you have no more electrons, no additional electrons there, because the electrons are emitted and going to the anode. Okay, let's do again, but looking to this one. You increase the number of electrons, then you reach the time when you reach the field, the voltage at which electrons are extracted from the carbon nanocone and sent to the anode. So you can make different things. You can determine, of course, the extraction voltage. You can determine the density of the change of density of electron in the nanocone before emission, okay? And then after, you observe the current. So which we were thinking, okay, we can even try to see whether electrons are passing there, but it is almost impossible because you should make time-resolved experiment for it. Okay, so, sorry. Oh, sorry. So here is the plot of the number of electrons, the increase of the number of electrons in the tip, in the carbon nanotip as a function of the extraction voltage, okay? And then when you reach the field emission state where electrons are passing through, of course, you have a stable one. And then you have this access to the charge evolution and also the distribution, because if you have a look to the fine structure of this curve, you see there is actually two regimes. There is one regime here and another one here. So meaning that, and this is in the direction of the tip, meaning that you have more electrons located in the vicinity of the tip than close to the starting point of this tip. Okay. And then you have the field emission and you can combine them. So actually, maybe I have 30 minutes more, right? Okay. So I will move to the magnetic part. I was thinking this will take me 1 hour and a half, but tomorrow it will be longer, so I will carry on the magnetic stuff. But maybe before, you may have some question on this electrostatic part. I don't know. Question? Yes?
Can you use this holography to image the plasmon waves in some
The
material?
plasmon?
Yes.
The plasmon wave. No, but the plasmon is dynamics. You know, it's dynamics. So I don't think you can see plasmons. What you understand, because there are plasmons are wave changing. So you have an oscillation of electron gas in the plasmon. You will see that with Raoul, I guess, this afternoon. This is going to do low loss, so you will work on the plasmon. But no, you cannot, because this is wave changing. Okay. We are dealing with electrostatic. so static means static. But this could be possible actually if we are thinking about making, but it will be in the future, maybe long future, but future, to make time-resolved experiments, to combine, if you are capable to start a wave, okay, and arrive not with a continuous electron beam, but with a pulse beam, okay, and you are making it stroboscopically, you understand, time-resolved experiment, pump probe experiment, you should be able to make an hologram at the time you have the wave at the given position, every time. So maybe that could be, but for the present, no. But this is something that we have in mind, actually, if we succeed in making time-resolved microscope.
Okay, more questions?
Like in a core shell structure, it's possible to differentiate the density charge contribution of each element?
In a core shell structure, we should be able to determine this core shell structure because of the minima potential, which are different. So this has been done. I have no example here, but you will see. Is there a tableau? No? Is there a tableau? No tableau. Yeah. Okay, you will see. You see my image at the very beginning when I saw. Up. Okay, if you have a core shell structure here, you will have kind of a starting like that at the beginning, and then you will have some change and going back, okay? And you can extract and separate and simulate and then get information about the fine structure of these core shell materials, both morphologically and even if there are very different materials, the minimum potential of each of them. So, but there are results on that I can give it to you. This is possible.
Regarding that carbon nanotubes guns, how they were modified? Means, have you modified field emission gun? Means cold fake or Schottky fake, or how they were modified? Means
this experiment I was showing is done on a Techni microscope, whatever. This is just to prove that we can use that field emission gun.
So it's a normal cold fake, yeah?
Yeah. So what we have done, but I didn't show and speak about that, is that we use this carbon nanocone and put it in a gun on a Atashi microscope to use it as a new sources, and it works fine because Atashi tried to. We are in very good contact with Atashi, and probably in a few years you will have this kind of carbon nanocone in Atashi microscope. Almost sure. But
energy resolution?
Energy resolution is almost the same because it's a field emission, so it's 0.3 electron volt energy resolution, but it's much more bright. So if you want to make some energy resolution, you need to use a monochromator, and you know that if you use a monochromator, you are losing a lot of intensity of the beam. But as this carbon nanocone is much more bright, then you still have sufficient electrons. So this is the goal.
More questions? Then, well, we can continue then.
No, I will carry on, so by chance.
Yes.
Holomag. Because the second part will be even longer, so it's fine if I can start today. So just tell me it's about 10 minutes or 5 minutes before 30, and then. Okay. So this is same introduction as yesterday. Up. So now, yesterday I spoke about electrostatic field, but actually that was a few words. So I will focus on magnetic field now, the way of using electronography to determine magnetic field. So this is my example previously, holograms and the phase image, and try to separate these two terms, and I was speaking about this term, and now I am going to speak about this term. So remember that I showed this Aharonov-Bohm equation, which links the phase shift of this electron beam with the electrostatic potential and the magnetic induction, and I told you that the electrons are sensitive only to the component of the magnetic induction which is perpendicular to the beam direction. Okay? So, and we are working in an electron microscope. And electron microscope lenses are magnetic lenses. And the main important one is the objective lenses. And the objective lenses is the lenses, and you are putting your samples in a pulpis of these objective lenses. Okay? And you know that this magnetic lenses is used to bend the electron beam in order to have an optical characteristic like any lenses. And the way you do that is with coils in which you are sending current of the objective lens, which create magnetic field, and the magnetic field you are creating in the objective lens is a magnetic field oriented almost parallel to the electron beam, and it can be very huge. It can be up to 2 Tesla at 200 kilovolts when you are using in high resolution mode the full capacity of the objective lens. So imagine you are arriving with some kind of materials, magnetic materials, teeny magnetic materials, nanocubes, in the pulpis of the objective lens, and then you are putting 2 Tesla like that. So if you have a magnetic material, the magnetization of the materials which will align with the magnetic field of the objective lens, okay? First, you will modify the configuration of the magnetic materials you wanted to study. Second, if you want to do holography with that, as the phase shift is only sensitive to the component of the magnetic field of the induction which is perpendicular to the electron wave, you have no signal at all. Okay? Meaning, if you want to do electron holography or even Lorentz microscopy on magnetic materials, you have to switch off your objective lens. Okay, so you have to switch off the objective lens. You're losing resolution, so you have a huge instruments which cost millions, and then with the major capability is the objective, and then you stop it. So complicated. So sometimes you may add lenses which are located below your sample, and then you can use this objective Lorentz lenses, so-called Lorentz lenses, to get some magnification of your object. This is still possible, and there is different way. Now, this is the first problem of working on magnetic material. You have to switch off your objective. Second, as I said, when you are making some holograms, you are measuring the total phase shift. So you have this electrostatic contribution and the magnetic contribution. And this one, most of the time, it's much more smaller than the first one. And you are interested in this one. So you have to find a way, and there is different, to separate these two contributions. Okay, first point, first problem, objective switch off. So this is a gel microscope. So this is the coupe of the column, which is a column. You have this condenser part, the objective part, the projection part, and you have your sample, which is located on the objective. And when you, in the objective, as I said, you have a huge magnetic field, okay? And if you have your sample there, it will saturate. So the idea of Lorentz microscopy and electronography is to switch off this objective, and you use a Lorentz lens, which is located below the objective lens, below the sample, and you can have some resolution, okay? Sometimes, with dedicated materials, you can reach 2 nanometers resolution, something like that, maybe, I would say more 5 nanometer resolution with this microscope in Lorentz mode, meaning without any current in the objective. There is other configuration. This is the microscope we have in Toulouse. This is a Techni corrected microscope, and what we have done I don't know, have you heard about CS correction yet or not? Yeah, okay. Well, on this microscope, you have an image CS corrector, which is located just above the objective. That was the first prototype sold by FEI, so before Titan. And what we did, we used the first transfer lens of this stacking of the corrector as pseudo-Lorentz lens, okay? And then we get some resolution about 5 nanometers as well. So this is not a dedicated microscope for holography of magnetic materials, but we managed to modify and use in a particular condition this CS corrector and work with the first transfer lens as Lorentz lens. The last things that possible is the very last microscope we get from Hitachi. I show it differently. Is that we discussed with Hitachi in order to have a double stage capability. And what we have actually is 2 stages. This is the columns. So you have the gun, you have the biprism I spoke about, 2 other biprism. You have a corrector here. You have the objective lens there. It's a 200 kilovolt. And then in this position, when you switch on the electron, the objective lens, you have the huge magnetic field here. And the idea that we had, that Hitachi had, is not to switch off the objective lens and put an additional lens, but to move these stages and put a stage above the objective lens, okay? And what we ask to Hitachi is to have these two capability. So in a case we are working in a normal mode, we have a 82 picometer resolution. This is a advanced corrected, high resolution corrected microscope with the B core. It is the corrector aplanator from CEOS put in this Hitachi microscope. This is conventional high resolution microscope with very good, sufficiently good spatial resolution. And in the case we use the upper stage, we have still 5 angstrom resolution because we are using not a dedicated Lorentz lens, but we are working with an objective lens, normal one, which is corrected in addition. And in this region, there is almost, no, there is not almost, there is no field. So we are in a field-free region, okay, with an objective and a corrector. So with this system, we get 5 angstrom resolution on a materials which is not embedded in any magnetic field of any objective. And I guess it's the best. Or maybe the Hitachi in the Tonomura project is better, but not so far. Okay, so this is the Hitachi microscope. And you see you have these 2 stages. So either you are working with this one, upper stage, or you are using this one, normal stage. And in this one, you are in a field-free condition, and you may have 5 angstrom resolution. And what you see there, 1, 2, 3, is the 3 biprism below the column. So this is the span. So we have, as I say, 5 angstrom in Lorentz mode, meaning without any magnetic field, and the sample is in a field-free space. And then what we measure about 1 to 2 Ørsted in this microscope, while in the other one we get, even when we switch off the objective, about 150 Ørsted. Okay, so this is the different way of working with the microscope in order to avoid having the sample in a magnetic region. Second question is, as I said, second problem is how to separate the electrostatic to the magnetic contribution. So there is different way. The one we are using the more is this one. Imagine that you have materials like that, which are given magnetization direction there. You are making an holograms, and you are extracting from this hologram the electrostatic part, meaning a potential, possible electrostatic charges, plus the magnetic part, okay? So you do the holograms, and then you switch upside down the samples, and you redo the hologram. And then, if you analyze the holograms, when doing so, you keep the same value for the electrostatic contribution, but you reverse in sign the magnetic contribution. So thanks to these 2 holograms, you can combine, and making the half sum of the half subtraction, you extract only the magnetic contribution and only the electrostatic contribution. So this is the best way, this is the usual way we are working to separate this. There is other way. The other way is modifying the accelerating voltage, because if you are modifying the accelerating voltage, you are changing only the electrostatic part through this constant, which depends on the electrostatic energy, while the phase shift of the electron beam after interacting with magnetic induction is constant. So again, you can manage with calculating the image. The main problem is that if you change the electrostatic contribution, you will change the alignment of the columns, so complicated. Because when you are making holograms, you have to align everything perfectly, and then if you change the voltage, complicated. So actually, this is possible, but nobody is using that. And the third way is also interesting. Sometimes we are using it. As I said, in the objective lens, you have a huge magnetic field. Okay? So what we can do, we can use this magnetic field to saturate the magnetic object in two different directions. And if these two directions are completely opposite, it can be used to separate the electrostatic and the magnetic contribution. So the way we go, you have these materials, magnetic materials. We have the objective on, okay? And then we tilt the materials, okay? So by tilting the materials, you are saturating the magnetization in a given direction, which corresponds to the projection of the applied, I would say, the magnetic field. And then you switch off the objective lens, go back to 0, and then you have saturate your system in a given direction. You make an hologram, and then you measure the phase shift, which contains these two terms. And then you go back to 0 again, and then resaturate the objective, but tilting the sample in the opposite direction, okay? And going back, switching off the objective, going back to 0, and then measuring that. And if these two configurations are exactly the opposite, okay, by image analysis again, you can have access separately to the electrostatic contribution and the magnetic contribution. So these are the three ways of extracting electrostatic to magnetics. But as I said, the one we are using the more is the one we remove the sample and switch the sample upside down and put it back. So the main problem is that when we are dealing with very teeny nanoparticles, which is most of the time what we are doing, if you are making an holograms on the materials that you have located the particles that are interesting, or you are taking a lot of particles, and then you switch upside down, you go back, you have to find back the exact particles. And then you can spend days of finding them. So you have make like, you know this game when you have to throw bombs on the boats, etc. Yeah, so you have to make a very precise map of where are the samples, etc. and try. Sometimes you succeed. Okay. So I show you that with this method we can separate from the phase image the electrostatic to the magnetic contribution. And I have to say that the first who did all these holography studies on magnetic materials is Tonomura, who passed away something like 5 years ago almost. And that was the first result he published on the magnetic induction you observed on this barium ferrite, I guess, particle, big one, 1 microns. So he was not looking on the magnetization inside the particle, but the stray field spreading out of these particles. Okay, so the spreading, and this is something that we can do, as I said. You are from this image looking to the contour here, isocontour of that. You have the information about the flux spreading out of these two iron nanocubes. And the equiphase, as I said, give the in-plane projection of the magnetic flux. So you get that. And this is similar to what maybe you at school have done that when you were young, like me, is that you have this little magnet, I don't know whether, and then you put a piece of paper on tip and you and you spread some limide of iron powder. And if you see the iron powder follow the flux line, and that's what you get macroscopic. This is centimeters, okay? But actually, this is similar to the in a nano world, I would say. Okay, so what we have now is that we have, sorry, where is this image? We have some images which correspond to the projection, actually, of the flux line in these materials. And from this projection, by making the derivative of these images in the direction x and in the direction y, we are capable to extract the component of the magnetic induction in the two directions. You see that if you are making the gradient of this magnetic image along the y direction, you get the component of the magnetic induction, the x component of the magnetic induction. And again, if you make the gradient in the x direction, you get the y component of the magnetic induction. So take this image, make the y derivative, and then you get the x component, okay, the component of this magnetic induction there. And if you make the y gradient, you get the x, the y component. And then you can combine. You have the x and y component of this magnetic induction at every point, and then you can draw this kind of a nice vectorial map where you see how the magnetic induction is spreading out of this object. And this is quantitative if you get the thickness, again, because you see that the thickness is appearing there. Okay? Okay. What I say? Okay, that's fine. So, message to take back home, I said, and have this message in mind for tomorrow, is by the analysis of these phase images after separating the electrostatic to the magnetic contribution, we are capable to get quantitative information on the projection of the magnetic induction. This is quantitative, this is vectorial, and many work has been published, and I will illustrate that tomorrow on different kind of system. Here, for instance, this is a nickel nanocylinder of about 15 nanometers, on which you have a domain wall, a strange domain wall in the middle, and then by making holograms and extracting the magnetic induction there and plotting the component of the magnetic induction, we are capable to see how is the fine domain structures of that. This is a work published by Rafał Dynen-Borkowski, where he saw the different magnetic configuration in cobalt polycrystalline materials which make different arrangement. So you see the magnetic induction in the cobalt nanocrystal and around it. This is some work that will illustrate tomorrow. So you will see either on iron palladium thin films, a magnetic tunnel junction, and this is done on Lorentz. So I will stop here, and tomorrow I have to check where I will be. Okay, I will illustrate some of the results, but this is done for today.
Okay, there are some questions from the audience.
Very nice talk. Thank you for this. By imaging the electromagnetic field, was necessary to change something in the theory of electromagnetic field or not?
No, for the present we didn't. You mean if we had some result that say no, this is not so evident?
Something rare, something that the theory doesn't explain yet.
Let me think. No, most of the no. We are actually we are pushing the method to analyze more and more in details the smaller and smaller objects. Now we are reaching the point where, as I said, we have 5 angstrom resolution, so it starts to be very interesting. And you will see that we have some results in the magnetic configuration of nano objects which were not expected. And then we show them, and then we try to simulate, and finally we find it by simulation as well. So it was not expected, but as soon as we find it, we can demonstrate that it was what. But in a term of really I mean, electromagnetism, I guess Maxwell law are still okay for Young. So.
More questions? Somebody? No? Well, let's thank again Professor Snoeck.